we have been discussing about optomechatronic system design and the key motivation behind optomechatronic system design, the overall evolution of the optomechatronic system design, and some of the key examples of optomechatronic system design, which includes the optical fiber based sensing, optical based actuation, then optical based data display, then about the data memory manipulation. So we have the optomechatronic systems are classified into three. One is called as optomechatronically fused systems, optically embedded mechatronic systems, and mechatronically embedded optical system. So we have discussed the application of all these three categories. Now we will discuss about some of the key components of optomechatronic system. So how these optomechatronic system caters to the entire system, microfabrication or micro robotic system. So it caters the different parameters related to micro robotic system. So one of the parameter is related to mechanism design, related to signal processing, related to sensors and measurements, related to microprocess, motion controls, artificial intelligence, a precision actuator, and the information feedback. So for all these parameters, these optomechatronic systems can cater the requirements, and appropriately it can be used for an integration. Now, when we try to see the function of this optomechatronic system, a number of fundamental functions can be generated by fusing an optical element with mechatronic system. Let us discuss one by one. First is with reference to sensing. So as far as sensing is concerned, we have the different techniques which are being deployed. Like we can use an optical fiber sensor for pressure measurement, for temperature measurement, for displacement measurements, accelerations, and three-dimensional imaging, optical motion capture, and confocal sensor. As far as optical scanning is concerned, the optical scanning devices, which includes a galvanometer, a resonance scanner, an acoustic optic scanner, a polygon mirror, a pan tilt mechanism, optical visual scanning system, navigations and surveillance robot, and the image recognition. So these are the some of the different functionality which can be catered under the optical scanning. Now with reference to motion control perspective point of view, we have the vision guide machine robot. Then under the vision guide machine robot, there is a well-designed tracker, a mobile robot, navigation, a visual serving end effectors, optical based motion controls, inspection heads, autofocusing, and optical based dead reckoning systems can also be deployed. Now with reference to optical actuator visual inspection, a hypersensitive light driven device, visual inspection device, endoscopes, ersascopes. With reference to inspection perspective point of view, we have the PCB pattern and the PCB solder joint inspection, a weld seam pattern. And three-dimensional shape reconstruction perspective point of view, X-ray tomography, X-ray radiography, a laser based material processing. With reference to laser based material processing is concerned, so we have a wide variety of spectrum, including the laser cutting, laser drilling, laser welding, laser grooving, laser hardening, laser based lithography, and stereolithography. These laser based lithography and stereolithography have been evidently used in the case of microfabrication related technique. Then with reference to optical pattern recognition, a target recognition, a target tracking system, and a vision based navigation system can be efficiently deployed. With reference to remote monitoring control, an internet based sensing control, a remote monitoring diagnostics, a remote visual feedback control can be deployed. Now overall, if we try to look into an optomechatronic system in robotics is concerned, the system that includes various mechatronic components in a mobile robot which navigation in a task environment. So in any mobile robot navigation, the optical visual perception unit display a crucial role because it provides the environment information for navigation. So here if you observe in this figure, so the robot can autonomously perceive models and maps the environment through which it navigates to carry out certain tasks. In other words, it can sense a three-dimensional shape, the dimension of the object, construct a map of the environment and recognize the object within the environment. This autonomous task execution is performed by an optical visual sensor and optical scanning system, a robot controller and a multifunctional software system. So, in all these cases, if you keenly observe, two different element, two different component will actively participate. So, one component is the light source and the other component is the detector. Now, when we need to look into the, if we need to look into the fundamental of usage of light source and the detector, let us take, like, we have an object in place. So, there is a light, this is a light source. From the light source, light is made to fall on the object. We get a reflection coming out of the object and it is captured by a detector or by a camera. Now, this is one way in which, like, we are trying to capture the overall features of the component. In the other way, what we can do is, there is a concept called shadowgraphy. Shadowgraphy is highly helpful to understand the overall boundary of a component, and it is also helpful for visualizing visualization. So, in this aspect, like, whenever we try to capture a kind of a complete feature, so there exactly such kind of camera based systems can be deployed. When we try to talk about a shadowgraphy, like, we can capture the overall background images using a shadowgraphy technique. Now, if we try to go into the closer view of this optomechatronic system, as I had discussed, we have a component, light source and a detector, which is nothing but a image acquiring system, a light source which is used for illumination, the plane at which the image is acquired. If the image is acquired over here, we call it as a shadow. If the image is acquired over here, we can consider it as a complete image which is coming out from the reflection. So, if we try to keenly observe, some of the key parameters which are used for getting a kind of a constructive images are, one is the type of light source which we are using, second is the illumination angle, third is the type of image acquisition system, fourth is the image processing. So, ideally, when we try to talk about the light source, there are different types of light source which exist. One is a kind of a monochromatic light source, where we have the lasers, LEDs, etc. And then we have a visible source in which a multiple wavelength interacts. Similarly, when we try to talk about the illumination angle, so with reference to illumination angle perspective point of view, either it might be an image acquisition or it might be a shadow. So, as far as an image acquisition is concerned, like if we need to have a complete details of the features, we can go for an image acquisition. In the case of a shadow, so the shadow is mainly meant for visualization of the structures. Like for example, so if I want to visualize the rate at which a micro robot moves, so there exactly the shadowgraphy plays a vital role. Now, when we talk about the image acquisition system, so under the image acquisition system, we have the detectors and the types of cameras. There are wide varieties of cameras which exist, like if we are more focused towards a visible spectrum, CCD cameras are available, whereas when we are focusing more on the thermal images or the thermal signatures, IR cameras are available or thermal imagers are available. If we are more focused towards some kind of images related to topography, then we can also use a kind of a hyperspectral imaging systems are available. Now, when we try to capture this image, these images are captured in pixels. So, ideally, like when these images are captured, so these pixels comprises of the photodiodes. So, what happens is when the image gets captured on this particular matrix, so the photodiodes get illuminated, and based on the illumination of the photodiode, like the image are being processed. Like there are different stages of image processing which are being deployed, like we might have heard about the binary image. This binary image ideally comprises of ones and zeros, which is nothing but either it will be black or it will be white. Like wherever the light falls, so it becomes a and the photodiode gets excited, it is considered as white, or in certain cases wherever the photodiode doesn't get excited, it becomes black, or it can be a vice versa phenomenon based on our requirement or based on the functionality. Now, this binary image can be appropriately converted in the form of a grayscale image. So, in the case of a grayscale image, like it has a shades of gray ranging from white to a complete gray. It is in the range of 0 to 256. 0 to 256 different shades will be deployed, and based on the different shades, so appropriately we can see the overall features what we are working upon. Now, these grayscales can be appropriately converted in the form of a color images, where these shades of grays are appropriately converted in the form of RGB. So, appropriate intensity mappings are done with reference to these RGBs, and through this intensity mapping, so we get a kind of a images what we are looking for. So, like during the capture, once we get it in the form of a binary, the transformation of the binary is converted into a gray, and from gray to a color, so that appropriately there are different steps which are involved, which involves the image reconstruction, edge detection, and then image thresholding, and image restoration, etc. These are the different steps which are been involved in it. So, we won't go in detail into those particular process. However, we will look into some of the fundamentals where how images are captured, how an optomechatronic systems are designed in such a way that it is used for an image acquisition, and how these image acquisitions are deployed for different sensing related applications. Okay. Now, let us take an example of a simple micro optomechatronic system. So, in this micro optomechatronic system, so this is a kind of a tube kind of arrangement. So, this is a kind of a small micro robots which is equipped with a piezoelectric actuator coupled with a camera, and then there is a tubing, there is a camera lid arrangement, and the moving guide, which is nothing but a kind of a propulsion which exhibits, and then there is a data transmission device which persists over here. Now, what happens in this is, like this piezoelectric actuators are deployed in this particular tubing kind of structure, and by giving an appropriate propulsion to the system, the movement of the piezoelectric actuators are monitored and appropriately captured. Now, when we try to observe the movement of these piezoelectric actuators, like these piezoelectric actuators are precisely used for controlling the focusing optics or the camera. So, like inspection or measurement of very small closed area is often very difficult due to the dimension problem of sensing and actuating units. So, micro sizing of such machines or systems can be achieved with the aid of an inherent optical sensing. So, a micro machine that inspects the inner surface of tubes in complex piping system such as power plant is shown in the figure. So, the machine consists mainly of a micro CCD camera, which is a kind of 10 mm in dia for visual inspection, a piezoelectric driving actuator, and a microwave based energy supply and data transmission device. So, it can travel straight and in a curved metal tube with a minimum diameter of close to around 10 mm is the overall size of the systems. So, these kind of systems are mainly meant for certain amount of inspections. It has a capability for a data transmission, either it might be a wired base or it can also be a wireless based system. So, appropriately data are transferred and then it is being captured. Now, when we try to classify the overall configuration of these MEMS based optical sensors, these MEMS optoelectromechanical systems or optical microelectromechanical systems combines optical component with microelectromechanical system technology. So, the micro level mechanical elements with micro level motion manipulate the optical signal by actuation provided by electronic structures in a system called as MOEMS. So, as far as in this MOEMS is concerned, it is well connected with an electronic system. It is also well connected with the, so it has a collaborative impact from electronics to mechanical and optic system. So, ideally there are different types of such kinds of MEMS based optical sensors which are being deployed for different functional applications. One which includes a kind of a Mach-Zehnder interferometer. Then we also there is a kind of a micro cantilever which exists, and optical tweezers which are used for micro manipulation related applications. So, we have a fiber Bragg grating. So, these fiber Bragg gratings are highly sensitive gratings which are used for different sensing related applications. Then there are ring resonators are there. So, the main function of these ring resonators are to sense as well as to generate high frequency systems. Let us go one by one. So, as far as an application perspective point of view, these optomechatronic systems are highly used in optical communication on LiDAR systems and optical measurement and inspection systems. Ideally, it is more suited for biomedical imaging and surgery related systems. So, more amount of applications are towards laser material processing systems. In fact, we had discussed about microfabrication. So, in the case of laser based microfabrication for the laser based patterning or for laser based micro 3D printing, for establishing the complete manipulation unit, such kind of optomechatronic system plays a vital role. Then we have an optical sensor automation which exhibits towards manipulation, towards actuation and as well as towards sensing. Then there is a kind of a robot assisted robotic vision and AI assisted imaging which will cater the complete image acquisition, image processing and image restoration activities, and it also has a capability since to compare with reference to the reference image and give an appropriate requirements or the appropriate decisions for different activities. For instance, like today we are talking about this autonomous robots which are used for moving in a particular platform, and when there is an obstacle is there, appropriately based on the size of the obstacle, it tries to take a boundary and it tries to move along the boundary for the efficient path planning. Now, let us discuss about this optical based displacement sensor. So, as far as this optical based displacement sensors are concerned, so these displacement sensors are used to measure the movement of an object and the occurrence of a reference point. So, the displacement sensor can be used to measure the amplitude, to determine the height, thickness and width of the object in addition to the range of the motion. So, when optical sensors are used to measure the distance to an object by measuring the time it takes for light to bounce back off the object, and it is defined as an optical displacement sensor. So, as far as in an optical displacement sensor, when we try to consider a generic construction, there is a sensor named as LDS, which is called as laser displacement sensor. This laser displacement sensor comprises of a source and comprises of a detector. So, from the source light hits the surface and it comes back to the detector. Now, for example, if I want to measure the change in the displacement, or there is a kind of a circular disc. So, in this circular disc, if I want to measure the linear angular orientation, these kind of LDS sensors can be deployed. So, these LDS sensors are efficient enough in such a way that it can be deployed in any kind of systems, and there are a small level LDS sensors are also available which can be used for kind of a micro displacement or a micro analysis. Now, let us discuss about the different principles which are deployed for this typical optical displacement sensor. So, the optical displacement sensors are categorized based on their working principles as well as based on their applications. So, the main types of optical displacement sensors includes the triangulation based sensor, the interferometric displacement sensor, a confocal sensor, a time of flight sensor and an optical encoders. There is also a particle sensor which works on the principle of shadowgraphy, which we will be discussing. Now, let us talk about the triangulation based sensor. So, as far as this in this triangulation based sensor is concerned, let us consider a laser transmitter lens is available over here. This lens is used for focusing the light on the object. Now, we are the light which is focused on the object is reflected through the lens and it hits the line sensor over the detector. So, the working principle of the optical displacement sensors are based on the triangulation measurement method, where the light source measures the surface and the line sensor form a triangle. These known as a triangulation laser or laser displacement sensor, which measures distance to an object fast and accurately. The laser or LED diode, a concentrated light beam, is projected on an object. The light is deflected in all directions by the surface of the object. A part of the deflected light is caught by a special line sensor with small photosensor in a row or fixer. When the deflected part of the laser beam fall on the chip is exactly dependent of the position of the object. So, a displacement of the object causes the displacement of the light on the line sensor. So, ideally, this is a kind of a laser spot which is being integrated and on the pixel, and these are kind of a line sensor. This is a representation of a line sensor detector. Now, these triangulation principles has a potential application towards analyzing the displacement or measuring the displacement of a micro robot within a particular boundary. So, within this particular boundary, if we need to measure the displacement, such kind of triangulation based system will be highly helpful. Now, let us talk about the interferometer based displacement sensor. So, this interferometer based displacement sensor is quite an interesting technique where we are splitting the beam of light into two, and then we are using a superposition principle to create the interference. So, if we look into the overall configuration of this interference based sensor, so there it has a laser source, then there is a beam splitter, and then then we have a moving object, and the interference are collected by a detector array. So, what happens is, from the laser source, the laser beam is splitted, and then it is made to pass through the beam splitter, where the beam is splitted into two. This acts as a reference region, and this is the area or the parameter which we need to measure. So, ideally, we will be measuring the displacement over here. So, since a laser source is used, it can be used for measuring the displacement on a microns order. So, in this particular case, we have a reference region, and then there is a moving object which is available. The laser beam is splitted into two. When the moving object moves back and forth, there is going to be a superposition of the image. This superposition of these image will result in an interference which is observed over here. So, the overall interference looks something like this. So, here there is a kind of an alternative dark and bright fringes are available in this interference pattern. So, when we try to change the displacement of the moving object, appropriately there is the fringes will get enlarged, and based on the enlargement in the fringes, so we can estimate or change in the alternative dark and bright fringes. So, appropriately we can estimate the change in the displacement. So, since the overall interference change is going to be highly on a micron level, so there is a need to integrate a detector array in the system. So, this detector array will completely record or completely measure the interference, and appropriately it gives a readout to the system. So, as far as this interferometric displacement sensor is concerned, this involves splitting a coherent light beam into two parts, a measurement beam and a reference beam. The difference in the distance traveled by this beam create a phase difference which results in an interference pattern when the beams are combined. Like good example of an interferometer which is widely used for different applications includes a Michelson's interferometer, which is used for different vibration sensing, micro displacement sensing, pressure sensing, etc. So, next important sensor is called as a confocal sensor. So, as far as these confocal sensors are concerned, these confocal sensors are advanced optical instrument which is used for precise displacement, distance and thickness measurement. They operate based on the confocal principle which involves focusing light onto a target and detecting the reflected light through a pinhole or similar aperture. So, a broad light source is focused on a pinhole which is imaged on the sample surface as shown over here. So, this is the overall construction of the confocal sensor. So, in the case of a confocal sensor, we have a light source, then there is a pinhole arrangement which is available over here, and then there is a beam splitter arrangement, a lens stack system and the sample. So, like the main function of this confocal sensor is to measure the displacement, the distance and the thickness of this particular sample. So, a light source is used. The light source is made to pass through the pinhole to remove the unnecessary, to have a focused beam, and these focused beam are made to pass through the beam splitter. From the beam splitter, it is made to pass through the lens stack. So, within the lens stack, once it reaches the lens stack, it hits the sample and the reflected beam is bounced back. So, here there are two things are there. So, in the case of a beam splitter, so we will be getting one reference beam and the other one will be the beam which we will be getting it from the sample. So, these will be passed through a kind of a spectrometer. So, using a spectrometer, we can analyze the overall characteristics of the sample. So, ideally, like due to the chromatic aberration, each wavelength is focused in different image plane. So, the reflected light is directed towards a spectrometer using a beam splitter. In this receiving light path, there is a second pinhole which ensures that only light that was in focus on the sample surface passes to the spectrometer. Now, the recorded spectrum exhibits a peak at the wavelength corresponding to a sample distance. So, the next configuration is called as a time of flight configuration. So, as far as in this time of flight configuration is concerned, so in this time of flight configuration, we have an emitter and we have a sensor. The photon hits the target and then it reaches the sensor. So, the distance between the one plane and the target plane is considered to be a distance d. So, the measured distance is the photon travel time by 2 into speed of light. So, this time of flight sensor measures the distance between the sensor and an object by calculating the time, and it takes for a signal typically in the infrared light to travel from the sensor to the object back. So, these kind of time of flight measurements are effectively used for dynamic analysis. It gives a complete, so whenever a micro robot is moving or whenever there is a need for analyzing the micro manipulation in a micro robot, such kind of time of flight sensors can be efficiently used to investigate the overall micro manipulation behavior in detail. Okay. So, like that is the precision of this particular system is evident from the parameters including a photon travel time and the speed of light which is measured over here. Okay. Next, we will discuss about the shadow projection sensor in the upcoming classes.